Those of you who don't know who I am, my name is Christopher Imler. I work for Michigan State University. I'm an extension agent. Some of you might be familiar with extension agents because you have a farm or your parents had a farm, and sometimes the extension agent would drive by and take a long lunch and talk to your parents or talk to you about crops, about timber, about livestock. My job in that role for Michigan State University is talking to folks and extending the science behind consumer horticulture. What consumer horticulture is basically your yard, my yard, their yard, all of our yards together. When we take them as a total acreage, it's actually quite a large area. It's millions upon millions of acres, right? So when we think about what the state is interested in, what universities and scientists are interested in, it is the safe and sustainable productive use of land, right? That's our mission. And so while we do great work in the commercial sector, the consumer sector is just as important when we consider that all of our actions combined can have a really big effect, right? Because all of our yards combined have so much size to them, right? A commercial producer has so many tools in their toolbox, right, for getting help, for getting good information. But what we've found is that consumers are really left out, high and dry. And for the most part, you're really reliant on, we are really reliant on what a manufacturer tells us, what the manufacturer of a product or a service tells us, whether it is appropriate for our needs, whether it's going to accomplish what we think it's going to accomplish, or even just how it works. So my job is to kind of pull the haze back over all these things and kind of cut through and add a third voice, an objective voice, about the science as it pertains to consumer horticulture products, right? And consumer horticulture practices, like hydroponics. This summer's theme, I believe, is water. And in keeping with that theme, I wanted to talk to you today about three really critical components of water that make hydroponics work, right? We have samples of some little systems in the back. I'm going to guess that most of you probably at least Googled what hydroponics was before today. But just to be thorough, right? Hydroponics is the art of growing plants in a soilless medium, right? And that soilless medium can be a lot of things. It can be rock wool, right? This is the same material. You want to be careful with this. I'm going to hand it around though. This is the same material that insulation used to be made of, right? That's safe. It's just if you get too much on your hands, it gets annoying. Rock wool, right? That's one thing that can be hydroponic, soilless media. I like to call these my Cocoa Puffs. This is expanded clay. This is another hydroponic medium, a soilless substrate, right? And the idea here is that the manufacturers, they have casts, and they make these tiny little pebbles, and they fire them. I'll pass this around, and you can grow hydroponically out of that. Have a feel. Okay, so that's our second one. And then our third one is just water itself. Right? We can grow hydroponically without soil, out of the soil, by suspending plants in the water itself, right? So this is my root system, right? It's stabilized with a little bit of bark chips. We'll say this is my hydroponic solution. And to do hydroponics, this goes in there, right? So the key here is no soil. Why does that work, right? If we don't understand how it works mechanistically, right? If we don't understand which gears are turning, it's just going to remain magic, right? And the thing is, as a consumer, as veteran consumers, we already know that everything that we don't know about a product or service, everything we don't know is going to be used against you by default, right? Everything that you don't know when you're going into the mechanics to get your tires changed, to get your oil changed, is going to be used against you. Anything that you don't know about hydroponics from a fundamental level is going to be used against you to buy or a product or service that you don't need. So let's talk about three things that you absolutely do need, though. Three things. This is generally how I do my workshops. People generally remember about 3 things when they walk away from something. So the 3 things I want you to remember today are 1, pH, 2, EC, and 3, DO. pH, EC, DO. You can say it like that. You can make whatever mnemonic device you want. pH, EC, DO. pH, EC, DO. If you find yourself with that in your ear on the drive home, you can blame me, but that means I'll have done my job. pH, EC, DO. pH is the acidity of a solution, right? You might be familiar with it if some of our veteran gardeners know, right? How acidic the soil is. EC is a little bit less common. Excuse me. Cashew's fighting me. EC is a measure of dissolved solids. Take a look at my cup of tea here. I started steeping this in cold water about 10 minutes ago. It started as clear water, right? The color has changed because some of the smaller particles that were in this bag have dissolved and have suspended themselves, right? The water's still there. The components of the tea are still there. A physical change has happened, but a chemical change hasn't, right? So a chemical change is one substance turning into another substance. The water is still here. It's the same molecule it always was. And the small colloid, the suspension of the tea, is also still there. And they haven't converted into anything else. So, why is that important? Why is pH, EC, DO important? Because when we're thinking about this hydroponic nutrient solution, right, that we heard about on YouTube last night before we came to the class, one of the important things that makes it successful is what is dissolved in the water, right? Okay? What is dissolved in the water? EC stands for electrical conductivity. pH, EC, DO. Electrical conductivity. As a scientist, one of the questions we're always concerned with when we're studying something, right, from a chemical standpoint is how much, right? How much of something is here, how much was there, how much needs to be there. If I had to ask myself how much tea is in this cup of tea, that'd be very difficult to sit there with a microscope and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, and then do this thousands of times, hopefully, to get some good data. What we can do instead is pH, EC, DO. What we can do instead is say, well, we want to know how much tea is in here, right? We know that if we add a little bit of something into the water, right, there isn't a chemical change, there's a physical change, but the behavior of the water changes, right? So, if we know that for every gram of a substance goes into this water, something else about its behavior changes 1 unit, we can make a mathematical connection, right? And we can actually see that even though this water started out at 0.0001 units of electrical conductivity, right? How well it conducts an electrical charge, right? Remember in high school you put the salt in the water, the light bulb turns on, right? The electrical charge. This solution in here, right, for me having added this tea into it, has become more capable of holding an electrical charge, all right? So electrical conductivity, all right? We're going to go a little bit further into each of these terms. I just want you to get into your mind early on what it is we're talking about when I say pH, EC, DO. All right, so EC, electrical conductivity, right? How much electricity can pass through the water, right? Per gram of tea that I've added, or fertilizer, or salt, or whatever. All right, 3 things, pH, EC, DO. We said pH was acidity, we said EC was the electrical conductivity, right? How well a charge will pass through the water based on what's been dissolved in there. The last thing that we're concerned about with pH, EC, DO is the DO, it's dissolved oxygen, okay? Dissolved oxygen is exactly what it sounds like. When things go into water, they can do one of three things. When one substance goes into water, it can homogenize, which means that all of the particles are evenly spread out. They diffuse, right? Your dog farts, right? It starts to smell a little bit better over time in the living room. They can settle, like they did in my water, right? Everybody knows what settling is, right? Or they can suspend, okay? Settling on the bottom, suspension in the middle, okay? Settling occurs in two places, and it occurs at the top and it occurs at the bottom. The last thing it can do is dissolve, okay? What I mean by dissolution is that not only has the tea kind of homogenized itself out, right? It's all the color, it's not more darker here, more darker here. It's spread out. But that tea is still essentially the same, right? When something dissolves in water, though, when it actually fully dissolves in water, the shape that the molecules, how they associate with each other, that changes, right? And how the water molecule positions itself against the oxygen molecule, that changes, right? I've got an example here of 1 cup of water that I've been aerating and 1 cup of water that I haven't been aerating, in the blue. If I were to take a dissolved oxygen meter, let's just pretend this is a dissolved oxygen meter, DO, because we said PHECDO. If I took a dissolved oxygen meter and I put it in here and it said, okay, Chris, you got 50 units. If I put it in here and I owned a $500 dissolved oxygen meter, which I don't, I would say that based on how much air is moving, through this air pump and this air stone, we would see 5 to 6 times more, right? Than the amount of oxygen right out of tap water. Now, let's add something else to that equation. If I took my plant and I did hydroponics, right? And it's only in the water, the root systems are only in the water, does that dissolved oxygen level go up or does it go down? It goes down, right? So just like you and I need oxygen to breathe and to live, presumably, plants also need oxygen. We need the oxygen for animal cell respiration, right? That's the act of how our cells break down sugars and turn it into energy. The same process goes on in the roots of plants, right? They're receiving sugars from the leaves, from photosynthesis. Those sugars are transported down, okay? And they're metabolized into active energy. They need oxygen to do it. So, if you don't have a source which is actively adding dissolved oxygen, DO, back into the water, because what we said 3 things were pH, EC, DO, if you don't have something which is actively adding oxygen back into the water, right, through bubbling, disruption, through oxygen injection, over time, the plants that are in our hydroponic solution, that oxygen goes down and down and down and down into the point where they're actually suffocating, right? They don't have oxygen to turn the sugars from the leaves that go down to the roots. They can't turn that sugar, right, into active energy to grow, okay? So, that's DO, dissolved oxygen. So we said pH, EC, DO, all right? I'm going to talk about this until you're sick of it, all right? pH, EC, DO, these are the chemical components of water, right? The chemical components of water, the pieces of the ingredient that make a nutrient solution work. It has to have the correct pH, the correct EC, and the correct DO. pH, EC, DO. Okay, those are the fundamental terms that you need to know for the rest of this to make sense. If I made 2 of you panic, it's okay. Right? This is for your benefit mainly. Acidity, dissolved solids, it's an indicator of fertilizer and other things. Dissolved oxygen, okay? All right, so what do we do with this information? pH, ECDO, we know it's important. We know that we need to tweak them. We know that there's a little bit of maintenance here to make hydroponic systems work. I don't want to talk about every single hydroponic system today. I don't think it's important because everyone's going to be doing something different. Instead, what I'll do is I'll talk about the things that are common throughout all of hydroponics. Okay? So regardless of whatever it is you're going to use, whatever it is you're going to try, or if you're just interested in reading about stuff, this will be universally applicable. Okay? Let's start with pH, from pH ECDO. Okay, so we said that pH is the measure of acidity, right? You taste something tart, that's very acidic. You taste something that's bitter or acrid, ugh, right? Nobody likes that flavor. That's basic, okay? Excuse me. So acidic, basic. Acidic, basic. I want you to visualize it this way, okay? I've got my blue liquid over here, and I've got my orange liquid over here, okay? If I was to draw a line between these two cups and number them 1 to 14, this would be 1, and this would be 14, okay? As I move from my orange liquid, my acidic liquid, to my basic liquid, right, my blue liquid, from 1 to 14, I become less acidic, more basic, right? So my number goes from 1 to 14, as it increases, it becomes more basic. As I go from 14 to 1, I become more acidic. Okay? Lye, battery acid. Right? Polar opposites. So why is this so important? Why are we going to talk about pH from pH ECDO? When we don't have appropriate pH for pH ECDO, hydroponics doesn't work. You can do a lot of cool things with hydroponics. You can manipulate plant growth. You can do things like change the color and the saturation and the intensity, right? You can grow plants indoors. You can grow them year-round. You can grow things that are finicky. If you don't have a nutrient solution which has the correct pH, none of that will happen, okay? When plants are grown in soil or in soilless solution or just water, and the pH is incorrect, what happens is all of my little fertilizers, right? Say this is my fertilizer. I've taken my little bag, okay, and I said, okay, it's got that much nitrogen and that much phosphorus and potassium, just like any other fertilizer. I mix it into my water here, okay, and I go, okay, that's my hydroponic solution. I put the fertilizer in there like the manufacturer recommended, and I'm going to put my plant in, all right? Plant goes in. Okay? And then I was even smart enough, I checked I was supposed to have an air stone in there. All right, good. We're good to go. What I didn't do was check the pH of the water after I mixed my fertilizer in. When that pH gets too high, as it inevitably will, right? pH of solutions goes up when plants growing them, right? This plant's growing in here. Not only is the dissolved oxygen going down, the pH is going up. When that pH goes up high enough, the chemicals, the compounds that make up, right, the fertilizer ions, right, the nitrogen, the phosphorus, potassium, which is what those 3 numbers on the back of the bag stand for, here as well, right, 3 numbers, nitrogen, phosphorus, potassium. When those molecules are swimming around, they're associating with each other, they're changing forms, they're reacting with oxygen. When that pH is wrong, from pH ECDO, when that pH is wrong, those compounds start to become unavailable to the plant, right? So all the nitrogen and phosphorus and potassium in the world added into my hydroponic solution, if it's the wrong pH, it will be chemically unavailable to the plant, right? There are different reasons why that works. Sometimes they make a slight reaction in one direction or another. They form a strange isotope. Sometimes it's the plant, just the mechanisms which take up the fertilizer just don't operate very well at a certain pH. There's a lot of different reasons. But one thing that we know for sure about pH from pH ECDO is that if it's wrong, you will never, ever get a plant to look like it was grown hydroponically, let alone survive. Okay? So where does that leave us? So we know pH is really important. We know why. We know how we know why. What can we do about it? The only thing that you can do to make sure that pH is appropriate, 6.0. That's the most generalized middle of the road guess. You have to get a pH meter. You have to get some kind of sensor that can check pH. You can't do hydroponics without this tool. It's impossible. It's absolutely impossible. I've taught this class at university level. I've had people who tried to do this a little bit more organically by shooting from the hip. You cannot measure the acidity of water by guessing. It doesn't happen. If you really have to go low tech, you can buy what's commonly used for pools. This is a pH indicator. Okay? You use this to check the acidity of a standard residential pool. And then the way this works is you get your little sample of your hydroponic solution. All right? Let's say I dipped into my hydroponic solution. Here's my sample. Here's my cap. I take my indicator, just like any old pH test. 1, 2. Make sure you shake it up. Okay, and phenolphthalein, which is exactly how it's pronounced, phenolphthalein reacts to change colors, right, depending on the pH of the solution. So this is kind of green, and the bottle says, okay, you take a look at it, and it says it's green, so I'm up in the 8 and the 8.5. I said earlier, 6 is our general range, between 6 and 14. Here's the thing. A 1 unit difference on the scale of pH units is a 10 times difference. So if I go from a pH 6 to a pH 7, right, which is which direction? pH 6 to pH 7. Orange to blue, right? I'm coming more basic. If I go from a pH 6 to a pH 7, that's 10 times more the basicity. Not acidity, but the basicity. So it doesn't seem like it's a lot. But if you're noticing even a half unit change in pH, you need to do something about it. Okay? So we said, first, you need to either have pool strips, can work, it's tedious, but some kind of way to test the pH of the nutrient solution. Either an indicator solution or a meter like this. These really are not expensive. 10 bucks. You can get these for $10 on Amazon. Are they laboratory grade? No, absolutely not. You're not going to win the Nobel Prize for hydroponics using one of these meters for sure. And nobody is, but the great thing is, the difference between my $400 meter that I use to calibrate $10 meters is about less than 1/10 of a unit, right? I have to use this for work. I have to. But nobody needs it. For what you're trying to do, for the accuracy that you need for consumer hydroponics, buy one of these, use it till the wheels fall off, buy another one. All right? The way that you can make these work better for being so cheap, right? Like buying a Walmart knife and sharpening it to a feather blade. Use calibrating solutions, use standardizing solutions. These are industry standards. To calibrate these meters, right, the manufacturer has its own instructions, but it will always call for one of these solutions, right? All pH meters in existence in the US use a 4 pH and a 7 pH calibrated solution, right? These little packets that you normally buy to do that come with the machine, they are so expensive. Do yourself a favor, this is $3, this is $3. If you buy this meter, buy the calibrating solution for it. Sometimes you'll see a 9 or a 10. This is a $10 meter. If you're measuring anything over a 9, you don't need to worry if it's a 9 or a 10. It's way too basic, right? Buy the 4 and the 7. That's all that you need, okay? Don't buy these little packets because for the price of 3, 4 of these, you can buy the solution itself, Okay? So, we said pH is important. It's important because fertilizer, right? The way we deal with that is we get a sensor, cheap pH meter, right? $10, wherever, right? You don't need the fancy one, but you do need the calibration solution, right? Okay. So we know how to detect our pH, right? Something is off, something is amiss. We're up in the 8s, the 8.5s we said for, where was our water? Over here. Way too high, right? Way too high. What do? Well, we add a little bit of acid, okay? This isn't like the Grateful Dead kind of acid, right? This is a weak acid. This is a citric acid, okay? Here. This is a relatively benign chemical, but I don't wear safety glasses thinking that everything is going to turn out fine 100% of the time. Okay. So, I need a volunteer. Can someone go up and give me a hand? I just need you to hold the meter and read out the concentrations. Perfect, come on up. Okay. Alright, here, I want you to hold that, and I want you to take a look at the pH. Okay. This is my $300 meter. I've got a lot of confidence in it. Okay. And I want you to tell me what number you're seeing right now. We'll stir. Okay.
7.63.
7.63. What did I say we wanted to be at? 6.5 is fine. Okay, so I'm going to take my acid here. This is citric acid, pretty benign. Add a little bit in. Give it a stir. Okay, what's that number doing?
2.5.
Oof, way too much. Okay, so I made my hydroponic solution too acidic. There are two ways that we can do this. We can do this the complicated way. Hold that for a second. And I can say, okay, I went with the pH down, I screwed up, I'm going to use the pH up. And then we can play this game of up and down and up and down and up and down. Or we can do this the easy way. Check this out. Number?
2.53 is going up slowly. 2.64.
Perfect. But you get the idea. Instead of trying to play this, this game of going up and down and up and down and up and down with the pH up, the acid, and the pH down, right, which is our base, the easiest thing to do is, if you make a mistake like this while you're mixing this stuff up, just dilute it with water, right? You're going to use it. You're definitely going to use it again, okay? Okay, thank you very much. Right. So, we know why pH is important, we know what it does, we have a general idea of where we want it to be, regardless of the system, right? Regardless of how you're mixing your hydroponic nutrient solution, if it is a big kiddie pool with floating foam and lettuce, versus if it is a drip irrigation system running over, oh, my expensive meter, a drip irrigation system running over coconut core or some of this nice rock wool, right? We have to test the pH, right, after we mix the fertilizer in, okay? And if the pH is off, we have to adjust it down with an acid, we have to adjust it up with a base. Any questions about pH? Cool. Okay, let's go on to EC, which is what we said is the second component from, don't make me say it. Three things. pH, EC, DO. All right. EC, electrical conductivity, or as I like to tell my students, how salty is something? Okay? Because when we mix these fertilizers in, if you've never seen a water-soluble fertilizer, that looks a lot like salt, right? It looks a lot like some kind of road salt, rock candy. And that's because from a dictionary standpoint, it is a salt, right? It's an anion and a cation, right? The chemicals that make up this fertilizer, right, dissolve in water the same way that table salt dissolves in water, okay? So, when table salt dissolves in water, we know that the EC goes up. Therefore, the more fertilizer that goes in water, the EC also goes up, Okay? Just like our pH, we want to be sitting in this kind of sweet spot so that the plants can take up as much fertilizer as they need, but they're not stressed by the salinity of the water from adding too much of this stuff in. All right? So, we said that pH is important. We want to measure it, we want to change it. EC is important. We want to measure it, we want to change it, right? So let's take a look at another neat little tool. Also important, but this is one of the things that you can maybe get away with not owning. This is an EC meter, okay? I bought it from the same company. I think it came from the same box. Yeah. Bought it from the same company. I think it was $15 for both of these. It's an EC meter, right? And it's going to check how salty the water is. Okay. So I am reading in units 4.2 EC. All right? 4.2. No, sorry, 0.42. 0.42. Just like pH, we generally want to be around 6. For EC, for electrical conductivity, we generally want to be around 1.5 to 2.5. Okay? 1.5 to 2.5 millisiemens, like millimeters, millisiemens. Siemens is a measure of conductivity. S-I-E-M-E-N-S, Siemens. Okay? If we are at 0.4, right, that means it's not salty enough. It's got to go up. Okay? So just like with our pH, we're going to add some fertilizer until it is at the right level. Ooh, that's crusty. We're going to add a bunch in, okay? This stuff is incredibly concentrated. We're talking a tablespoon a gallon to get to 1.5 pretty often. Okay, so we took our fertilizer, we added it to our hydroponic solution. Stir, 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 stir. It's really important if you're mixing this stuff by hand. If it's cold out, especially cold, you want to stir the heck out of it. Okay, so we hope that that's dissolved. We take our meter again, our EC meter, we put it in. Here we go. Now I'm sitting at 1.98 millisiemens of conductivity. Now we're at 2.0. All right, we're on the money. So 1.5 to 2.5. Right? Here's the thing. I know I showed you the pH first pH ECDO. When you're making your hydroponic solution, do the fertilizer first. Always do the fertilizer first. Here's the thing. When you add the fertilizer in, the pH is going to change a lot. All right? It's going to change a ton. When you add the acid in, the EC will only change a little bit. So, if you have to do something, you do this last, because this is going to cause the least changes that are unintended. You do this first, because if you pH modify the water before the fertilizer, you're just going to have to do it again. So mix your fertilizer first, right? Check it with your EC meter, because that's electrical conductivity, how salty is it. Get it just right. Dilute it if you need to. There's no other way to do that. You can't take the salt back out. Throw a potato in there, maybe. But check that. Dilute it down. Then do your pH. All right? Okay. So I said 1.5 to 2.5. How do I know when it needs to get changed if I'm not measuring it every single day? One, you wait a week. Wait a week or two to change it. You'll develop kind of a feel for how rapidly it happens, right? But what are the things that are going to make it more or less often that you need to add more fertilizer in general? The higher the temperature is, the more the light intensity is. So let's say you've got really bright lights and you crank them up for a day. Anything that makes a plant grow faster is going to make it take nutrients up faster. So let's say I'm in the cold, it's not particularly bright. I'm going to expect plant A, cold plant, right, to grow a little bit more slowly and to work down the nutrients in the solution more slowly, right? Now if I take plant B, and I put plant B in the heat, right? it's next to the furnace, and I'm using a really, really bright light. I expect this plant to grow a lot faster, and therefore take up nutrients a lot faster. All right? So temperature and light, anything that's going to make these plants grow faster, they're going to use up more nutrients. Okay? All right, that's EC. Any questions about that in general? Remember, easiest way to do this is you get your fertilizer, you mix it in first, and you check with your $10 Amazon Prime meter. All right? 1.5 to 2.5. Question over here.
There's another number I know that's connected to the EC.
Sure.
And I want to say it was TPS, but I could be.
Right, so TDS is total dissolved solids. So here's the interesting thing about that. Electrical conductivity is the measure of how a charge moves through a solution, whereas TDS is the actual measurement of how many particles are in a unit of mass, right? Because some ions and some things, when they're dissolved in water, they don't impart the same conductivity, right? So the 1 gram of tea powder that I've dissolved in here will change the conductivity of the water to a lesser extent than if I added in an actual salt, right? Because this is a much better carrier of electrons and a moving charge, right? So a TDS meter is essentially the same, but if you want to split hairs, right, and you want to make this easier, the exact opposite. If you don't want to split hairs and you just want to make this easier on yourself, buy an EC meter, right? If you buy a TDS meter, it won't read out in millisiemens, it'll read out in parts per million, right? But because we're only concerned with how this fertilizer changes the water, we don't want to measure the effects of all the other things that are changing in there. Because there's algae, there's bacteria, there's even aquatic fungi. We don't want to measure those changes. We only want to measure what's going on because of the fertilizer. Because that's what we can control, right? Okay, any other questions about fertilizer? Yes?
What about the water that you start with? Not water softened, I'm assuming.
Yeah, so if you're starting with municipal water, well water, chances are the alkalinity will be different, right? The alkalinity and the acidity are two completely different things. And unless you have a water softener, right, you're just kind of stuck with whatever it is, right? If you have a very, very alkaline water, that means the pH is going to change more rapidly because of carbonates and bicarbonates that are dissolved. That's a longer talk. Suffice to say that you're probably going to have perfectly fine water, because the thing which makes water unsuitable for plant growth also makes it unsuitable for human consumption. So it's kind of like temperature-wise for your house, you really don't need to worry about what the temperature is, for example, because whatever's comfortable for you will be plenty for the plant, right? So in terms of your starting water, the only thing that you can really do is maybe check the pH, right? You can check online with the municipal government, but you really just want to check it with your pH meter that you bought for $10 on Amazon, right? 15 if you get the combo pack. They don't pay me anything, they should. Any other questions? That was a great question though. Starting water, also very important. Okay, and then our last thing for the 3 important things from pH, ECDO is DO. Dissolved oxygen. There are 2 ways to do this, okay? You can either make sure you have enough by having more than enough, or try to risk having not enough and then always ending up with too little. I'm always a fan of adding more oxygen than I need versus not enough. Oxygen is fantastic because in terms of the hydroponic solution, there's no way that you're going to screw this up. I guarantee you, there's no way you can screw this up. You are financially incapable of screwing this up, because you would have to buy a French nuclear physicist's research lab equipment in order to get enough oxygen super dissolved into this water to harm this plant, okay? The easiest way to figure out what you need for dissolved oxygen is to look at the pump, okay? This is a 8-liter oxygen pump. Okay? When you're growing in just water, right? Like I have my plant just floating in this water using one of those hydroponic systems. All you need to do is match the volume that the pump is rated for, right? Sometimes it'll be rated in gallons, like a 5-gallon, a 25-gallon. You match this number to the amount of hydroponic solution that you're oxygenating, that you're aerating. So if you have a 10-gallon reservoir, a 20-gallon reservoir, or a 20-gallon system that the hydroponic solution is going through, right? Match that number to the number on the pump, and that's it. Will you have more oxygen than you need? Yes. Will it become one less thing that you have to guess about? Also yes, right? The way that you can make this work a little bit better is adding an air stone, right? I'd say that if you had a 10-gallon reservoir and you were using a 5-gallon air pump, you could probably get away with those numbers if you add an air stone. But they've got to be in good condition. You have to check them often, because the thing that makes this air stone work is all those bubbles, right? It's pushing air through the water, right? And that bubbling action that's right there is dissolving oxygen in, okay? So, oxygen is important, way too expensive to measure, even for me. You're not at any risk of adding too much oxygen. And the easiest way to figure out if you're getting enough is to match the size of your reservoir to the pump, okay? Gallon to gallon. You want to err on the safe side, get a little air stone, okay? Cheap, easy insurance. All right. So, the only thing that's really left to say about dissolved oxygen is on warm days, there is something that you want to be generally aware of. And that is if your growing space, or if you're doing this outside, or the water's hot for whatever reason, the rate at which oxygen dissolves, oxygen comes out of a liquid, and the rate at which CO2, like CO2 comes out of a liquid, those rates change at really high temperatures. What that means is, for every molecule of oxygen that I'm pumping in here, on a hot day, there's even more CO2 going in there and dissolving in the water. That wouldn't be important normally, except for the fact that when CO2 goes into water, it becomes carbonic acid, right? So let me take my air stone out, turn that down. I'm going to read the pH. Now, no one saw me put anything in either of these, right? These have just been sitting in front of us. Let's take a look. 7.38. It's not very hot in this room. Nope, not long enough. 7.38. Here we go. Just need to switch it around more. 7.27. Okay. So, even just doing this, there we go. Even just doing this for less than an hour, I think I've had it on, I've already changed the acidity of this water, right? And we're going down with that number. So, what that means is, the dissolved oxygen, although it's super important, if you accidentally overdo it, if you have a lot of air pumps going and it's on a really, really hot day, you might cause your pH to come down a little bit over time. Easy fix, you just stop aerating so much, you turn the pumps down a little bit and you let it come back up, you take the air stones out, right? Or you turn the temperature down in the room, right? But we said that because pH is so important that we want to, as much as we can, know what it is and then change it back towards that 6.5 range, okay? So if you haven't noticed yet, there's a little bit of a balancing act going on here, right? With this nutrient solution. We're adding things in, we're sometimes taking things out, we're dissolving them, but we're trying to balance what's going on in terms of the acidity, the fertilizer, and the oxygen, or the pH, the EC, and the DO. Okay? That's all the information I want to dump on you today. I don't think it's particularly helpful to overload people's brains with new ideas without giving people time to metabolize.